Hi everyone, this is a continuation of 6.2. So in the first video, we did the disk method to find volumes of revolution. And now we're going to be doing something called the washer method, which is just an extension of the disk method. So before we were just working with one curve that was being rotated around either a vertical line or a horizontal line. And we were using disks, so areas of circles that we're adding up to calculate the volume. Now we're going to be rotating an area between two curves instead of just one curve, and still rotating it around a line in order to create a solid 3D shape. So this time we're going to have two curves, like I said. So we're going to have an outer curve, one that's farther away from the line of rotation, and then an inner curve, one that's closer to the line of rotation, okay? And when you rotate it around, you see that you create what's called a washer. So if you don't build things, you might not know what a washer is. It's basically just a circle or a disc with a hole in it, okay? So the outer disc that's created is like this, right? And then the inner disc that's created looks like this from the blue curve. And so we're interested in calculating the area between the two discs, which maybe I'll just, and adding that up over the region from A to B, or whatever the bounds of our integral is, okay? So let's just look at our next example. We're going to be rotating around the x-axis. So we're going to be drawing these discs from left to right. We're going to be integrating in terms of x between these two curves. So I'll label one. So this curve, the straight line here is y equals x. That is the top curve, or the one that's farther away from the rotation axis. And then we have this one that I'll show in green here. This is y equals x squared. And that's the one that's closer. So that's going to create our inner radius. Okay, so let me just draw one sort of, I'll draw. So that's going to rotate around. It's going to kind of look like that. And then the outer curve is going to rotate around and kind of look like that. Well, that's not the best drawing. Let me try again. Okay, let's see. This is more like, to make it, it's nice to draw it as best as you can so that you can really visualize it. There we go, that's better. That's going to be kind of my inner radius. And then that's going to be more like the outer radius. Okay, that's better. Okay, so let's label these. Our outer. It's going to be the y value of that particular curve, right? The distance from the x-axis to the curve vertically. So for that red curve, y equals x. And the inner radius, don't want to clutter up my drawing too much, but is going to be the y value for that green curve, and it will be y equals x squared. Okay. Let's just try and visualize this. I'm going to show you an animation really quick. So here is the region. It's kind of flat so that you can see it. You can see it over here on the left. We've got y equals x and x squared. So we've got the parabola and the straight line, and we're going to be rotating it. Let's see what happens as we go around. I'm going to keep going. Oops. So you can see the kind of shape it's created when you do that. Let's try it over here too. So when we spin it, like I said, it's really slow because it's like a lot of work for the computer to do when you do these animations. Let's refresh it. Maybe it'll be better. Maybe not. Okay, well, that's fine. I'll link these animations. Oh, here we go. Okay. So I did 0.1 x squared just so it's bigger. And x Okay, so that's similar to the region that we're rotating. So I just want to give you an idea of how it looks when you actually rotate it. Oh, it doesn't want to go. Here we go. There we go. It's going now. It goes around like that, and you can see how it sort of looks, right? So it's kind of like a cone, but then it's hollowed out in the center. So when we calculate the area of each, so let me just draw this here. So outer radius of each washer is going to be the red line, so x. The inner radius is going to be x squared. And my bounds for my integral are going to be from x equals 0 to 1. You can see that on the drawing there. So my volume is going to be from x equals 0 to 1 of the outer circle area minus the inner circle area. So that's how we get the area of the washer. So it would be pi times r out squared. So that's the outer circle area minus pi times r in squared. And so for us, it'd be pi times, so the outer radius is x, so it'd be x squared. Oops, I had too many equal signs there. Minus pi times x squared squared. I can pull out a pi because there's a pi in both terms. Just simplifies things a little, and it'd be x squared minus x to the power 4. Okay, so I'm going to evaluate this integral now. That would be 1/3 x cubed minus 1/5 x to the power 5, evaluated at 1 and 0. And so you can plug that in yourself, and you should get 2 pi over 15 as your exact answer. Okay, so let's just review. This is the formula that you want to use every time with your volume of discs, or sorry, washers. So you're going to calculate the outer disc and subtract it from that inner disc because it's being hollowed out. So our outer radius was x, our inner radius was x squared, and then we completed the integral. Okay, let's do one more example, last example on this video. So this time we're going to be creating washers that are stacked vertically. So we're going to be integrating in y. And I've added another complication. We've moved the radius, sorry, we moved the axis of rotation over. So we're rotating around the line x equals -1. Okay, so let's just draw what this shape would kind of look like. It's going to be, so we've got this outer radius. I'm going to use the same colors. Red, I used outer time. Okay, so the outer radius is, or the outer curve is here. It's farthest away from the axis of rotation. So if I rotate that around, it's going to kind of go like this. Okay, so it should be exactly symmetric on the other side. And the inner curve is this line here. So, and then that's going to kind of look like this. So we're actually using the same two curves that we used in the exact other example, but this time we're rotating around a different line. Okay, so let's try and draw what a one washer would look like. We'll do our best. So they're pretty big. So that's the inner circle, and then the outer circle, my shaky hands, looks like this. Okay, so I'll shade the part we're trying to find. We're trying to find the area of that shaded part in black there. Okay, so this time we're going to be writing everything in terms of y. So let's talk about the inner radius first. There's two parts to it. Okay, so this part here, okay, is the distance from the curve to the x-axis. That would be the x value of that curve. And then this part here is an extra piece that's been added on because we're rotating around the line x equals 1. So it's going to make our radius for every single washer larger by 1. So the radius of the inner curve is going to be x plus 1. The x value of the curve plus an extra 1 because we're rotating around the line x equals -1. And the outer radius, I'll do it down here, is also the x value of the curve plus extra 1. Okay. For the green curve, okay, let me just write down the formulas. So this was y equals x, and this one was y equals x squared. So I'm going to rearrange both of these in terms of y, because we're going to need to write all our radii in terms of y, because remember, we're stacking these washers up vertically, so we're going to be integrating in y. So this, if you rearrange it, you take the square root of both sides. X is the same as square root of y. And when you rearrange this one, it's just for x equals y. So x equals y there. So the outer radius and inner radius can be written as, our inner is going to be x plus 1 or y plus 1, since x equals y for that curve. And the outer radius is x plus 1 or root y plus 1. I'll put in brackets since x equals y for inner curve. And then in brackets since x equals root y for outer curve. Okay, great. So we've got our inner radius, we've got our outer radius. Our bounds for the integral are going to be in terms of y, and we're integrating from y equals 0 all the way up to y equals 1. And you can just tell that from the graph. So our volume is going to be from 0 to 1 of pi r outer squared minus pi r inner squared dy. Because we're stacking vertically, we need to integrate in terms of y. And so we get 0 to 1 pi times the outer one is root y plus 1 minus pi times y plus 1 squared dy. We can pull out the pi because it's just a constant multiple in both terms, and also we need to expand those brackets in order to do the antiderivative. So I'll have a pi out here. Root y plus 1, if you expand that all out, you get y plus 2 root y plus 1. And if you expand this one, you get y squared plus 2y plus 1. And now we need to collect like terms before we do the antiderivative. We also are going to write the root y as a power instead of with the square root, because it's easier to do the antiderivative. So I'm going to write the largest exponents first. So I'll have negative y squared minus y. The ones actually cancel out, and we have plus 2y to the half. I'm going to make sure that that is right. Yes. Okay, dy. And so the antiderivative of that is negative 1/3 y cubed minus 1/2 y squared plus, so power bumps up by 1, divide by the power, so you get 4/3. And we're integrating between 0 and 1. I'm not going to plug all that in front of you. I've already done it on my calculator, but you end up getting exactly pi over 2. Okay. So disk method and washer method are both very similar, but basically the difference is just that for the washer method, you have 2 curves. And so when you calculate the area of each washer, it's the area of the outer circle minus the area of the inner circle. Other than that, they're pretty much the same in that when you're stacking your discs or washers vertically, you need to integrate in y, and when you're stacking them left to right, you need to integrate in x. Okay, so again, there's no textbook questions for this section. The assignment is just attached.